To start, so as first speaker for today, we're happy to have David Berenstein. We're going to talk to us about aspects of AdS CFT dictionary.
Thank you. So I'm just going to give you a warning about today's talk. Is that, and most of the talks that I'm going to give is that I'm not really going to explain how to do calculations. So that's number one. And I'm going to try to keep it conceptual and give you a picture of what we think we know. But there will be some times when it gets a little bit more nitty-gritty. You just have to accept that some of that is part of the pain that's necessary to kind of proceed and understand what's going on. Okay, I'm very glad to be here. It's always good to come back to South Africa, my third time. So it was good to see the writers and yesterday for those who were with us. So I'm very happy with what I've seen so far. It's a great conference. So I'm glad to be part of it. Okay, so let's start with the basic statement of the AdS CFT dictionary, or the AdS CFT correspondence, is that quantum gravity can be equivalent to quantum field theory in fewer dimensions. This is a very deep statement. In classical physics, you would never be able to say this, because they obviously have a different character, and then one of them is, let's say, classical gravity, and then the phase space would come. How fast the phase space grows with, let's say, some random stuff, and it grows a lot faster from field theory in some sense. So this statement can only be true in some quantum sense, and it's what's at the heart of what people call holography, that somehow the physics of gravity can be encoded only asymptotically in the boundary. Okay.
I'm not sure that phase-space comment is relevant, but anyway.
If you do a naive specific heat, you get the wrong counting.
Okay.
So if you do a specific heat of a field theory in 10 dimensions, you get the wrong counting. Yeah. That's the statement. That naive volume counting of specific heat will give you the wrong answer in one relative to the other. Okay. Again, it's a statement that's kind of like that. To be more precise, local conformal field theory in d dimensions can be equivalent to gravity in anti-de Sitter space in d+1 dimensions. And then conformal field theory is what makes it anti-de Sitter. If you do things that are not conformal field theories, it's things that are not quite anti-de Sitter. Things that can be ascribed in the UV by conformal field theory are things that can be ascribed in the UV by anti-de Sitter. And we need to explain what that is. So that's some notion of asymptotics, high energy physics. And there can be extra dimensions. So the dictionary does not say d equals d+1. It says d equals something of d+1 plus extra structure sometimes. Okay. And this is a quantum equivalence. And what we say, what we mean by quantum equivalence, is that they have the same Hilbert space. And this can be a completely trivial statement because the L2 functions, or the infinite Hilbert spaces, are all equivalent to each other. So that's not enough. You have to have the same symmetries, meaning the same generators of symmetries, meaning the same algebra of symmetry. And then you need to have that the representations of the algebra on both Hilbert spaces give rise to the same representation theory. So they need to have the same action on the Hilbert space, and you need to be able to translate from Hilbert states in one side to Hilbert states in the other one. So one of the things that's usually the symmetry is the Hamiltonian, so they have to be isospectral. They have to have the same Hamiltonian. But there should be a dictionary that lets you move from one to the other one and tells you how to compare states that are described in one formalism with states that are described in the other formalism.
Will you be requiring that the two sides are like fully consistent theories by themselves? Or
not quite. Right. Is that what we can calculate on one side can be related to what we can calculate on the other side? For some stuff. The dictionary is still a work in progress. This, in some sense, is still a conjecture. The mathematicians would not be happy with what we've proven so far. I think everybody who's worked on this on the physics side is absolutely convinced that this is the right statement. That doesn't mean that we understand how it works. And as we progress, I'm going to tell you what we know, and then what we don't know, and what the new tools that have been deployed to try to understand this stuff. So eventually we'll be talking about things like quantum error correction, some things of quantum information. And I'll explain roughly where that structure arises from and how to see some examples of it. Okay?
Sorry, I didn't understand your answer to the previous question. I thought when you said same Hilbert space, you mean there are two ways to get Hilbert spaces
from two sides independently, and they are the same.
Right, so the statement is that in gravity we don't know how to build a full Hilbert space.
Yeah,
But we know how to build pieces of the Hilbert space.
but in principle there's a theory.
In principle, if there is a theory that we can call non-perturbative quantum gravity defined independently, we should be able to make the map. What we know how to define is perturbative gravity around some background, and to the extent that we can match one background on one side to something on the other side, the perturbation theory that we can do on gravity should be obtainable somehow from the other side. So usually, this is what I mean by theory of quantum gravity, is something where you can at least do perturbation theory around some solutions, plus something that can match to it, and then that something that matches to it is what we call the completion if it is complete.
Although let's say supergravity, superstring theory in AdS 5 crosses 5, that is fully consistent and
we don't know what that theory really is as a theory of superstrings. We know what perturbative superstrings do, but we don't know what non-perturbatively superstrings really are. And I don't mean that we don't know that D-branes exist. We know that D-branes exist, but the theory of black holes has very nasty problems in string theory that haven't been resolved, and anybody that claims otherwise is pulling a fast one. The quantum information paradox has not really been resolved in practice, maybe in principle in some abstract sense, but abstract solutions do not tell us what happened. So I would not call that a complete solution of the information paradox. So, okay. So what I'm going to talk about today is how must the dictionary be structured to work perturbatively. And that means around the vacuum. And the point is that there's this Witten dictionary, and many times in a lot of articles and a lot of review papers and books, it's presented as this black box that lets you compare one side to the other one, and because you have a dictionary that tells you which computation is doing what, people have spent inordinate amounts of time just doing computations on both sides to the extent that they can, and basically comparing. And this is what people call evidence for the AdS CFT correspondence. But in some sense, there's this way of presenting it which makes it look like a black box. And what I'm going to talk about today is why this black box is not really a black box. It's the only way that can be sort of set up to actually make it work. So a little bit of it is how do we show that? And part of it is there was some conversation we were having with Antal Javicki yesterday, which is that it's all symmetry, right? So you use symmetry and you get it, but the question is, how do you deploy the symmetry and intuition to actually make it work? And it's not just symmetry. There's more in it than just symmetry. There's some ways of thinking that are very physical, that are part of how we actually can really realize that this is the only way that works. So on the conformal field theory side, the group is SO2, D. And what that means is that I'm working in D minus 1, 1 dimensions, and then you have to add 1 to both of them to get to the conformal group. So it's SO2, D. So it's a conformal field theory that lives in D dimensions, D minus 1 space, 1 time. And that's what this 2 means. If I go to Euclidean theory, it's SO1, D plus 1. So the symmetry, and when I tell you the symmetry, that has a specific way of thinking about it. The isometries of global AdS space are also SO2, D. So at least from the point of view of symmetry, there is something that we can match. There is the symmetry of the conformal group, the isometries of AdS space. If you're doing gravity, they're gauged. But you have to be careful with what gauging means. They're gauged kind of for small gauge transformations, things that have compact support. But usually the isometries of AdS extend all the way to infinity and act on infinity, and these actions on infinity mean that they're acting non-trivially on the Hilbert space. So in a certain sense, the isometries, even though they're locally gauged globally, they do contribute some non-trivial notional charge. And this has to do with the non-compactness of AdS. If you do things in compact space, you get into trouble. So if you do this for the sitter, you might find that things don't quite work because the symmetry group of the sitter is kind of gauged. So to make things work, you need to work harder to just get started. Okay, so that's that. So the states, how do we classify states? We take the symmetry algebra and we construct the irreducible representation of the algebra, and we try to figure out which irreducible representations are sitting inside the Hilbert space that we built. So the first step is just like in quantum field theory, you have to classify representations of the Lorentz group. Here we have to classify representations of SO2, D. And then, unfortunately, this was done already for us on Friday, so I don't have to do it for you. But before we study the correspondence, basically, we need to do a little bit of theory how to understand the states on both sides. Okay? So the tools to do so will be, on the field theory side, Valcourt variance, but the analytical continuations in space-time will be throughout both gravity and field theory. And this is an important thing, because this is what actually nails the dictionary to the wall and tells you how it works. So in the conformal field theory side, we're going to talk about the states there. So the first thing I have to tell you is how to organize the algebra. And then the usual organization of the algebra is presented in this way. There's the rotations, translations, and then dilatations. And then just for completion of the algebra, there needs to be something that has the same U index, and these are called the special conformal transformations. And what conformal field theory adds to Poincaré, which is mu and d mu, is these two guys over here, and this is what provides the extra generators of symmetry. More symmetry usually means more control. Okay.
Are you
So-
thinking to dimensions larger than 2, or?
Yeah, dimensions larger than 2. We're going to talk about AdS5, so usually we're... I don't want to do infinite conformal field
Larger
theory.
than 0, no. Why 2?
No,
Well, in 2 you have
it's not zero short.
Because in 2 you have more than that. You have the full stress tensor, you have complete...
But you could
It's
also
an
this.
infinite algebra.
So you could also study d equals 2 with only this.
Yeah, you can also study this just in the equal to 2, and this is what people call the theory of quasi-primaries, rather than theory of primaries of Virasoro. You do quasi-primaries of SO2, or yeah, SO2,
Yeah.
Okay. So, here's the other thing. So, this tells you that you can do rigid dilatations, but the idea is that if you have a symmetry, there's usually an associated current, and you can apply it locally in different ways. So you can actually do local rotations by your symmetry. That usually generates new states or new configurations. So one of the ways to think about conformal field theory is that you can do local dilatations, which we really interpret as taking a metric and doing a value scaling. And then the statement that you have symmetry associated to value scalings is that the conformal field theory on a manifold M with a metric G is equivalent to the conformal field theory on the manifold M with a value scale metric, this one. And then if you can do a change of coordinates on this one that brings you back to this one, you get a full symmetry of the conformal field theory. But otherwise, you could think of this as covariant under boundary scalings in the sense that you can relate whatever happens here to whatever happens here. And the dictionary usually involves powers of these things dressing all over the place. So the local boundary scaling kind of shows up. It's not eliminated. This is not binding variant, this is not covariant. Binding variant is that it's not equivalent, but it's identical to. And identical to means that this doesn't matter, and that's usually when we get into quantum gravity or some other stuff. But here really what that means is that you can translate from one to the other. Okay.
But here the metric is not supposed to be dynamical.
The metric is not supposed to be dynamic.
And isn't it supposed to be flat?
No.
For CFT?
Well, the point is that we're going to pick some manifold and some metric. So we pick flat space and flat metric, and that's the start. That's one way to describe a conformal field theory. But usually a conformal field theory can be placed on arbitrary manifolds with some metric. The metric has to be sufficiently regular to right? Singular metrics are kind of problematic for the usual reasons. But if you have something sufficiently smooth, you should be able to put a conformal field theory on it, and then work.
But I mean, it must have the killing, the conformal killing vector as isometry.
Yeah, so what determines how much symmetry survives depends on the conformal killing isometries of the metric G. Okay.
When you said Poincaré before, it is just a group of isometries of that metric.
Yeah, Poincaré is the group of isometries of flat space with flat metric.
Yeah.
Okay.
Maybe.
But that's usually what we call the local symmetry in this case. Okay. Observables. So this is another thing. If you do field theory in flat space, usually you do S matrices, but they do not exist for conformal field theories because they're plagued by infrared divergences. And that's the fact that you have massless particles. massless particles, they can be radiated in arbitrary amounts. So there's no natural notion of S matrix, which is usually you can think of S matrices as something that describes some sort of exclusive scattering amplitude. The only thing that exists here is inclusive, and even though you can get rid of some of these divergences in some setups in QED and stuff like that, what we mean by an S matrix there is not quite an S matrix either. It's something that allows for some noise of soft stuff dressing things, and you have to be careful what we mean by that. So the point is that the S matrix does not exist. There's higher divergences just because there's proliferation of massless particles. So to make statements that work, you need to introduce an infrared regulator. And this is just quantum field theory. Basically, you need to do things that are infrared safe. So the things that are infrared safe is not S matrices. Those are UV safe, but not infrared safe. Okay. So what can we also do? This while rotations, quick rotations. So we can do an analytical continuation. And the idea is that we can take the real time and analytically continue to imaginary time. Not while rotation, quick rotation. I just was tired when I wrote this. So the idea is that you should be able to analytically continue from real time to imaginary time. We do this in Feynman diagrams all the time. This is part of the analyticity of the properties of the Feynman diagrams. And it's the passage from field theory in real time to field theory in imaginary time. And we don't bat an eye, we're used to doing this. And we should be able to do it here as well. And then the Lorentzian conformal field theory should be writable as some Euclidean conformal field theory, and there should be a way to basically go from one to the other. Okay. So in the Euclidean field theory, you can write correlation functions of local operators. So you insert local operators at various positions. And the infrared regulator is the fact you have finite distances between these operators. So you have a finite distance, that means that that thing is going to cut off the infrared stuff at the distance scale at which things are separated, because everything else is too big, and then you don't contribute.
David, is it so obvious how to do the Vic rotation? Any theory can be Vic rotated?
No, it's not obvious. A chiral boson cannot be Vic rotated in a nice way. So for example, in 2 dimensions, in 1 + 1 dimensions, you can have a relativistic field theory of a chiral boson. The chiral boson, you can write some commutation relations that make it well defined. And the Wick rotation is nasty, and you have to add all kinds of extra stuff to make it more or less work. And then you need some proper differentials and Riemann surfaces and various other stuff. And this is what people who do topological field theory have learned how to do in some really nasty way for ages, and then you can write stuff.
And for sure it's a theory without, again, without any gravity, any dynamic.
And again, it's a theory without any gravity. Okay, so, but the idea is that, okay, the fact that you have finite distances between operators is what introduced regulator. And then this regulator gives you infrared safe stuff because it's regulated stuff, and the point is that this is a regulator that is imposed in some sense by the choice of physics that we're doing, and then the things that you compute here are infrared safe because they're cut off by these distances.
So you could also study correlators in the Minkowski theory, provided they are space-like separated. So
yeah, so you can do this in Minkowski space, but you get problems with Lycons, which is what a lot of the, let's say, new development is about, how to take care of Lycon similarities.
Right.
And here you don't have dilation symmetry, because otherwise the notion of distance would be a bit.
Well, the point is that the dilation symmetry can be used to fix the distance to some token value.
So distance.
It's covariant with respect to these transformations. So you can choose, if you have few points, you can choose one distance to be 1, and then everything else gets rescaled. So the covariance basically tells you that some actions of dilatations provide a word identity for this thing, which makes some calculations simpler, which is the type of stuff that lets you compute 2-point functions exactly. And then with the extra symmetries, you get the 3-point function story of so that's how you basically use those to basically solve this problem for low-point correlation functions. Okay. So you should all know this. This is stuff that you've been doing. All I'm telling you here that you didn't know, or that you might not have thought about too much, is that the fact that you're putting things at finite distance is providing an infrared safe way of doing computations, and it provides a regulator. Okay? It's a very important thing that you think about it carefully. So you can insert an operator at the origin. You can go to polar coordinates, and I'm going to describe now the operators, the correspondence. So the idea is that now in this Euclidean theory, you've just picked an origin, called it 0, and you put an operator there, and then because you put an operator there, you've singled out that place anyhow. Okay. So what we can do now is say, okay, why do I stick to flat coordinates? I can use any coordinate system because these theories exist on the metric with a space, but they don't automatically imply that you have some preferred coordinate system. Coordinates are just things that you can change. It's a passive thing. It's just a way to describe it in physics. So you can change to polar coordinates. So if I change to polar coordinates, I have the r squared plus r squared, the omega d minus 1, and this is a sphere. So I haven't done anything yet. But now I say I can do local vary scalings, and I can pull out a common factor of r squared, so this one and this one. And I can show that this metric is equivalent to this same metric over here, where I chop off this r squared. And then now I'm doing physics in the sense that I'm imposing the local Weyl covariance. So I can relate the theory on flat space with a puncture at the origin to the theory on the metric that's the r over r squared plus the omega d minus 1. And what we do is we introduce a tau, which is equal to log of r. And then when you chop off this r squared, this is the r over r, you think of this as the tau squared plus the omega d minus 1 squared. So I've just provided for you a Weyl rescaling from flat space in polar coordinates to a sphere times the Euclidean time, which is the cylinder. Okay?
So you change the topology, you say obviously r is 0 is something you have to remove, it's a puncture.
Well, the point is, the point r equals 0 is equivalent to tau goes to minus infinity. So you have to take a limit to understand what anything at 0 means. So if you think of tau and minus infinity, one way to think about it is the infinite past in the Euclidean sense. Okay? So the place has disappeared from the system. We've done a puncture. We've kind of changed the topology. But we still want to remember the fact that we have an operator insertion at the origin. So how do you put an operator insertion at the origin? You need to put a boundary condition at tau equals minus infinity that provides the information that you were naively losing by taking the limit. So the point is that an operator insertion can be thought of as a boundary condition at tau equals minus infinity. Okay.
But that's the way you would deal with a puncture too. So if you have a puncture, you say what the boundary condition is.
Okay. So the point is that I've told you that we allow weak rotations on this, so tau goes to minus infinity. It can be analytically continued to the imaginary time to tau, which is a real time go to minus infinity. And real time equals minus infinity is an initial condition. And then the point is that you're propagating things on shell. So an initial condition in the infinite past can be brought to a finite time by some propagation. So you can basically do that. But the idea is that you really have to think about this as a non-trivial boundary condition at tau equals minus infinity. So what you're saying is that in minus infinity, you're not in the vacuum. Okay. So if you do the classical theory on real time, you would say that this is classically equivalent to an initial condition in the far past. As I said, we solve the equation of motion on shell, the absence of sources, and to evolve the system from past to present, and at the present, an initial condition in the present time in quantum mechanics is what we call a state. So a state is you prepare your system, put some initial condition. The state is the thing that describes an initial condition in quantum mechanics. And then you do time evolution plus measurement, and then this is how you do quantum mechanics. So the idea is that what we call an initial condition in quantum mechanics is a state on the Hilbert space of states of the quantum field theory of the cylinder. So the list of local operators, properly done, and there's some issues there, is in one-to-one correspondence with states on the cylinder, but more precisely, eigenstates of the dilatation operator are eigenstates of the Hamiltonian, the cylinder, and then this one-to-one map of these things can really be done. And then you have to be careful when you do superposition of states because you might get something non-normalizable. And if you're propagating things in Euclidean time, things might blow up in your face. So you have to be very careful what we mean by a state. A state you can superpose arbitrarily in the Lorentzian theory and nothing will happen. Things stay kind of, probability is preserved, not so in Euclidean theory. So you have to just, there's some things that fail if you are naive, and mistakes can be introduced that way.
So sorry, is what you have just said, that you could start with a normalizable state and you evolve it, and at some point it's not normalizable.
More precisely, you start with a normalizable state, you evolve it towards the past, and then
Right.
you find a singularity before you hit tau equals minus infinity.
Right, okay. But that means that it couldn't come from a normalizable state at minus infinity.
Right, but that's, but the point is that the Hilbert space of states at finite slice is in one-to-one correspondence at the level of basis of states, and then some finite superpositions are also well behaved, but L2 completions are not. So it's this statement about these very formal states about quantum mechanics can basically ruin your life if you don't pay attention to them when you're doing things like this. Okay. Very good. So in a certain sense, if you take the typical correlator functions, they go like this. This is the typical 2-point function. It goes like 2 delta. And what you think is that when x goes to 0, this blows up. And this blowing up is the singularity that you're detecting in the Euclidean past. So the boundary condition in the infinite past is something that tells you that you're not in vacuum. And correlators blowing up is the stuff that tells you that you're really doing something that's not vacuum in the Euclidean past. Okay? So that's that.
Oh, isn't it the statement that two distributions at the same point is not really defined? I mean, you have quantum operators.
Right, that's part of the story.
In the field theory picture, that these are distributions.
Yeah, but the point is that this singularity over here is matched to a singularity I'm going to the Euclidean past of something else in the cylinder. So what that means is that the boundary condition at minus infinity is in some sense a type of singularity where if you were to describe it classically, you would say that the fields are not decaying towards tau equals minus infinity, but they actually blow up in a particular pattern. And the coefficient of those things will classify the states in some sense, but it's the statement that something is also needs to blow up in the Euclidean theory of the cylinder to describe the boundary condition. This is done at the level of operators. If you want to do classical physics, you can be more precise about how that works. I'll show that in gravity more precisely. Because what you need to do is you need to do something slightly different than this to actually make that precise. So this is better for classical states, and these are not classical states usually. Eigenstates of the Hamiltonian are usually not what you would call a classical state in classical physics. Okay, so here's the thing. Now we go to a new real time, which is what's called radial time, which is that tau we turn into IT, and then the new metric on the cylinder is minus dt squared plus d omega squared, and the manifest group of isometries is the SOD minus 1 cross R, and this is the way we kind of split the group to actually understand the representation theory of the conformal group, is that you take the conformal group and you actually diagonalize delta, that's what this is, and you diagonalize the SOD minus 1 of rotations that commute with that, okay? So the states are classified by the energy, which is called the dimension at the level of operators, and the spin, so it's whatever spin labels of SOD minus 1 you have. And this is the usual story that states have some energy and some spin, because these operators commute with each other. And then the standard representation theory is that P acts like a raising operator and K is a lowering operator in the cylinder. This is really important. So after these analytic continuations, the unitary condition is that the P is the dagger of K. Whereas if you start with the Lorentzian theory, P was self-adjoint and K was self-adjoint. So after these analytic continuations, we've changed the notion of unitarity. So the Hilbert space in the cylinder is not the same Hilbert space as the Hilbert space in flat space. Okay. So this is a technical point that is important. And then the idea is that when you have stability, negative energy boundedness means that your state has a vacuum and then there's some positive energy or a gap on top of the vacuum. The states are well defined. Implies that there's a ground state in each representation that's annihilated by K. So acting with K. You cannot keep on lowering the energy forever. You have to stop. That defines what's called the primary state. And then all others are obtained by the action of P, acting on that primary state, and they're called descendants. And the primary state is also classified by the dimension of the primary and the spin of the primary. So what that means is that if you have the primary, you can build a tower of states with deltas and spins that are deduced from the primary, and then that gives you additional classification. So usually when people talk about classification, they talk about classification of primary operators, and then the rest can follow from descendant relations, also known as word identities. So this is the plan. And then the operator state correspondence is phrased that the operator O is the state O, and then you can change on both sides. And the idea is that there's an action of conformal group on the left, and there's an action of conformal group on the right, and the state operator correspondence is that the two natural actions are the same action on each other. Here you act by commutators, and here you act by the usual stuff. But if you're more careful in the path integral, you know that a commutator can be written as a contour integral around the origin. Okay, that's what a commutator really looks like in conformal theory. And then when you go to a cylinder, it's an integral at a fixed radial time, and then that's the usual action of just one single operator on the state. So it's not a commutator anymore, but the two actions are the same. And then if one is really, really pedantic, one can go and describe how these two things are related. I don't care. But the idea is that from path integrals, if you're careful, you realize that the two actions of the conformal group are the same, and you should not have to worry about this. This is kind of a given. And this is the only way in which the operator state correspondence should work, is that the representations theory should really be the same. And you can talk about states or operators, and you go back and forth as need requires, and then you ignore all the red flags because you have something that does you describe.
So by path integral, you mean we act on the operator as if it was inside a correlator?
Yes. And by contours and various other stuff. Yes.
Is there a new constraint the second Stiefel-Whitney class of the manifold has advantage somehow to go from SO to spin?
Probably, but I'm going to ignore that for the time being because we're just talking about a cylinder and flat space, and I'm not going to talk very much about non-trivial manifolds with non-trivial metrics. So it is true that not every manifold would have any metric. You can put any field theory without some constraints depending on some spin content of the field theory. That depends on anomalies and various other stuff, so there might be things that where you're not allowed to do some naive things, and that would be classified as one of those things. But if you don't have fermions, usually you can do anything you want to. So it depends on whether you have fermions.
Typically you do concrete.
Yeah, but there's a free boson. The free boson you can put pretty much on any manifold.
No, I mean for a CFT.
For AdS, yes, but again, I'm not going to talk about much of that today. The fermions will appear tomorrow mostly because they appear in examples, and supersymmetry kind of carries them along for a ride. That gives you control. So it's one of those things that you pay a price, but it's not bad. So
are you going to talk about local operators?
the point is that the operator state correspondence is for local operators. You need the puncture at the infinite path so you can propagate things to infinite path.
Okay, so you're going to stick with.
Yeah, the operator state correspondence is about point operators with well-defined actions of the conformal group, and that are in some sense sufficiently well-defined so that certain superpositions survive. Certain other superpositions can survive at finite radius, but not like when you put insertions of operators separated at some distance inside some radius. There's some relation that you can build, but you might find the singularities sooner.
But we know that we also should extend to non-local operators. I mean, there are
Yes.
states which are.
Yes. Okay. So now let's go to gravity. So the point is that here we know what to do. We have operators plus conformal group action on the operators can be related to states on the cylinder. So the Hilbert space is the Hilbert space of states on the cylinder with a natural classification of stuff of the conformal group action. And we can relate these to a list of operators that you have here. Okay. So I haven't done anything. I've just told you how to do the classification in some abstract sense. So now let's do the gravity side. So what you have to do in gravity is, well, how do we do this? Well, the first thing you need to do is kind of say, okay, I have background and then I have fluctuations, so I have to write wave equations, and then I have to solve wave equations, and then how do I solve the wave equations? That's some nasty problem. And then the question is, and on top of that, I need to classify these things according to representation theory of the conformal group. Okay, so we saw some of this on Friday, how that works. But the idea is, what I'm going to tell you now is how to do this without suffering any pain at all. Okay, so I'm just going to build these representations geometrically in some nice way by just being clever in some sense, and then you realize that if you know how to do spherical harmonics, you know how to do this, and it follows rather easy. Okay, so the idea is that AdS is a type of analytic continuation of the sphere. So if you start with the equation of a sphere, y1 plus y plus 2 squared equals 1. So why do I do d plus 2? Is because AdS is going to live in d plus 1 dimensions, and I need a d plus 2 dimensional space, so that when I cut it with one equation, I get something of the right dimension. But other than that, everybody knows this is a sphere, and now AdS is where you take d plus 1 and d plus 2 and call it y0 and y minus 1, and put minus signs in front of it, and the analytic continuation is also that this plus 1 goes to minus 1. Okay. So I've done nothing. This is a way, this is one of the presentations of AdS-D, and it's the one that's kind of the wick rotation of the sphere. But it's a double wick rotation because I'm going into coordinates. Okay. That's that. Now, that's in the kind of Cartesian coordinate system of the embedding. I can also go to polar coordinates, and what I can do is choose the first k plus 1 coordinates, and then the other d minus k plus 1 coordinates, and decompose these coordinates, each of them in spherical harmonics, so sorry, in spherical polar coordinates, so I can introduce an r1 and an r2, and I have a dr1 squared plus r squared e omega k squared. That's one k plus 1 plane, and this is the other d minus k plus 1 orthogonal plane, and then I have the two coordinates, and then I can do r1 squared plus r2 squared, call that r, and decompose r1, r2 into polar coordinates itself. So I can do the r squared plus r squared d theta squared. And then r1 is r cosine theta, and r2 is r sine theta. So I can do something like this. And then I throw away the dr squared. Okay, so the idea is that since r squared is a constant, I can throw away the r part. And then I get some nice set of coordinate systems for the sphere. And now I'm going to explain the analytic continuation for k equals to 1. So I have two coordinates here and d coordinates here. And then the idea is that I take this stuff and I want to analytically continue in theta. And one of these things is a circle, so it has an angle itself. So I get minus d theta squared plus r squared cosine squared theta. This is just the analytic continuation of theta goes to I theta. And then this one changes sign. So theta goes to I theta, this one changes sign, but this one doesn't. And then sine theta has the same properties as theta when you do the wick rotation analytic continuation. So you get a minus sign and a minus sign here. And then r squared was equal to 1. And then you need to stick in a minus sign over here. And then that minus sign is the one that gave that minus sign, minus 1 for the analytic continuation size. So the idea is that if I now call theta rho, then I have cosine squared of rho, I have to change the sign here. And this was a circle coordinate, so I call that dt squared. So t is going to be the angle on that circle. And then I get the sine squared, sin squared rho squared the omega d minus k squared. And this is the standard coordinate system that's used in AdS, which is called the global coordinate system. Rho is a radial coordinate. This t that came from an angle is the time coordinate. And this one over here is the sphere polar coordinates for this radial decomposition. So I deduced these without solving anything. I just took the circle, the sphere analytic continuations, and then these analytic continuations, by design, preserve all the curvature conditions that you need that make the space a symmetric space, and that basically means you don't have to solve any equations to get this. Okay. Here's what we do. you call yd plus 1 plus I yd plus 2. So these were the two original coordinates that we had. What is really becoming y0, y minus 1. And you expand those as a radial coordinate times an angle. Okay? And then once you translate to the angle, this angle tau is going to become the new angle t. And then the arc cosine theta becomes cosine squared of rho. But the idea is that now you get this exponential like t over here. So this is the stuff that's going to give you proper functions that behave well with respect to time. So this is the stuff that gives you harmonic in time in the sense of having an into the identity. And the new variable rho is not compact. It goes from 0 all the way to infinity, so you have to be careful. So when you analytically continue these, the other coordinates, the yi for the complement, go to sinh rho, a spherical harmonic of something in the minus 1 dimensions, but this is a spherical harmonic for some flat coordinate representation. Okay. Very good. Okay. So a scalar function of a sphere can always be written on spherical harmonic based on the composition of spherical harmonics. Basically, it's the representation of the group of the isometry on the sphere. And they can be obtained from solutions of the Laplace equation in one extra dimension in flat space. So the idea is you put this sphere, there's a d omega squared over here, you take your favorite Laplacian equal to 0, and you make an assumption that your function phi is some power of r times ylm, and then you plug this inside here, and then that relates the radial behavior to the ylm behavior. And if you do this, this is how you get the j squared angular momentum values for all this stuff. So again, this is something that lets you bypass doing group theory the hard way. You're kind of cheating your way around it. You're allowed to do this. So the ylm can be thought of as symmetric functions of the y's. And I apply Laplacian equal to 0, and that means that A is traceless. And then the highest weight state is of the form y1 plus y2 to the L. And this is just why we introduce this complex coordinate. That's the one that lets you do the highest weight state quickly. And now we want to do the analytical continuation of this highest weight state to AdS. So this yd plus 1 plus yd plus 1, that d plus 2, goes to y0 plus y minus 1 to the minus delta. So L gets analytically continued to minus delta, z to minus delta. So the idea is that whereas before L was an integer, delta can now be a non-integer. Okay? So when I wrote this representation, the complex variable z is not really a single valued function when you go around it. Powers of z that are fractional are also allowed, and then that describes how to go to the universal cover of this kind of AdS thing, rather than sticking with this circle being of such 1 in this AdS thing. We need some conversions to infinity. What we call the operator k is the stuff that is y times something anti-holomorphic plus z times dy. So this is now a little bit of bookkeeping. Delta is the thing that measures the powers of z, bar versus the powers of z. So it's the counts the powers of z. And then the momentum is the stuff that gets analytically continued to this stuff. And then obviously p is the adjoint of k stuff, because they're related by complex conjugation. Okay? And this delta is going to be positive because we need things to converge at infinity, and the point is that z goes like Cauchy rho, and if you want things to be normalizable, things have to decay sufficiently fast at infinity to actually make it work. Okay, so this is just a way to get to the solutions without ever having to solve the wave equation directly. Okay. So the sets of harmonic functions at fixed degree, meaning if you take the spherical harmonics with a fixed value L, that's like having some fixed mass in the analytic continuation. The eigenvalue of the Laplacian is what we usually call a mass in some sense. So in this case, the analytic continuation tells you that when you're doing an irreducible representation, you have to fix the delta for the highest weight state, and then the rest of the representation follows. So if you have the highest weight state, you can build it. So let's go back to this representation. I told you that the highest weight state is z2 minus delta. Now you stick k on it and you see that it's 0 automatically because it's holomorphic, so this dz bar kills it, and it doesn't depend on yi, so this kills it. So I've solved it for you, those are the conditions. And then it's an eigenstate of z dz with eigenvalue delta. So delta, I get my eigenvalue, and then I add with p and I get everything else. Okay. Very good. So the set of harmonic functions of fixed degree, meaning fixed delta for the highest weight state, or fixed L plus L times L plus 1. There are homogeneous harmonic polynomials of degree minus delta. And they're polynomial in y1 through yd and z bar, but they are kind of non-trivial in z in the sense that they have this 1 over z to delta kind of sticking inside at the beginning. So they're not quite a polynomial in z, but they're polynomial in all the other variables.
Sorry, is delta positive or negative?
Delta is positive, but the degree in the usual sense is minus delta.
Because y has degree minus 1. Or
no.
sorry, maybe I misunderstood.
The point is that the dimension is to be positive, but it's z2 minus delta, so it's this minus sign over here that's defining that. The y is of degree 0.
Right.
Y dz is of degree 1 because of the...
Good. Yeah,
so
yeah.
it's just counting that. Okay. So delta is the powers of z, minus z bar. Okay. So there is a polynomial in these things. And these are solutions of wave equation in AdS with some mass. And the way we usually call the mass is the mass squared in Euclidean theory will be L times L plus D. This is what you get. There's the usual L times L plus 1 in dimensions 2, which is the sphere. But if you go to higher spheres, you get L times L plus D. The mass squared has a minus sign in that one because in the Euclidean theory, the Laplacian has a positive spectrum. So to get a pole or to get some one-shot condition, the mass needs to be negative. And then after the proper analytic continuation, this L becomes something related to delta, minus delta. So you get something that looks like delta times delta minus D. So the sign changes here because the L goes to minus delta. So this is how this formula gets. And this is how you get the mass squared equals delta times delta minus D without having to do any calculation. Okay? So this is the stuff that kind of was in the written of paper, but the point is that I've done it from you just from being more careful about the group theory without having to solve the wave equation directly. I'm doing it by analytic continuation. We're allowed to do this. And now you have to quantize, right? So the point is that once you have the solutions to the wave equation, you have to quantize them. So the way we quantize is that to each partial wave solution, you need to assign a raising and lowering operator. So to each one of these, you assign a single particle state in the bulk. So the idea is that you take your solutions to your field equations, do a decomposition in partial waves of those solutions, and attach raising and lowering operators to each one of these solutions with some normalization. And then if you're in the bulk and you're doing a Fock space representation of the physics, once you have the single particle states, you can build multi-particle states by acting multiply with the raising operators acting in your favorite time. Okay. So this is the second quantization of this stuff. So you need to have the partial waves, and you need to build these operators attached to the partial waves, and then you have to kind of work in the usual canonical quantization procedure. But the idea is that this is all kind of straightforward physics. We know how to do this. So now we want to do asymptotics, which is one of those things that when rho goes to infinity, all members of the same representation decay at the same rate. That's because the y's went like a sinh, z went like a cosh, and z bar goes like a cosh, and they're a fixed degree. So you get an e to the minus delta rho as you take rho to infinity, and they all decay at the same rate. So that means is that you take the exponential times delta times rho times whatever this function is in the bulk, then the limit exists. So this number exists as a limit. And notice also that what we call delta is IDT. So delta is the thing that generates translations in time, because z and z bar were written as e to the it and e to the minus it. And then when you plug this into the definition, you find that what we call delta is it. So this is the stuff that naturally gets interpreted as a Hamiltonian. Okay? Very good. Different descendants meaning different values of delta, usually give these different spherical harmonics and different Fourier coefficients in T. So they're eigenstates of different eigenvalues with respect to I delta IDT. Right? So the idea is that for large radius asymptotics, you can see that you can get all of the descendants by doing Fourier transform in T. And then you can get you can peel off the coefficients of each one of these descendants just by doing physics at infinity. And this is one of the usual statements of holography, is that you can recover something from looking at the boundary, in the sense that if you have a formal solution of the wave equation, and you take this limit, and you look just at the stuff at infinity, and you do the appropriate Fourier transforms of spherical harmonic decompositions, you get your list of partial wave coefficients in the full solution in the model. Okay, so all of this is to tell you that you can recover the solution by looking at infinity. So this is one of the statements about holography, is that you should be able to do that, but the reason is because we're doing physics on shell. So on shell, solving the equation of motions in the bulk translates to being able to read all the solutions by doing something on infinity, and this is automatic. And the way you get that this is automatic is because we did everything starting from the beginning in the proper signature for AdS, and we were studying normalizable solutions of field equations in AdS, and we're just taking limits. So all of you know this from Witten, right? But here it becomes very obvious that this is a straightforward thing. There's no mystery here.
Sorry, is then the statement that you can recover the full F from F tilde?
You can recover the full F from F tilde, and that's because F satisfies a differential equation in the bulk. But the point is that it's just representation theory that, properly done, doesn't even require solving the solution, the wave equation in the bulk. It's kind of implicit in all of this stuff. Okay, so different descendants give different Fourier coefficients in T, and then the angular momentum, the spin, gets related to the different partial spherical harmonics on the sphere, Fourier transforms in time.
Do you see that you're all looking to normalizable? Are you all looking normalizable?
Yes, all of these are normalizable because they decay sufficiently fast at infinity because it goes like z to the minus delta. So, and that's what controls the asymptotics.
That includes cases where you're like, these funny double quantization cases.
As I said, this is careful. This is in some sense engineered so that this boundary condition is well behaved. So that's what sets up the boundary conditions that you need to impose at AdS are implicit in the fact that I picked a particular highest wave state, which implies that it's right. There's two values of delta for a given value of m squared. So the implicit solutions already have some notion of what's the asymptotics at infinity, which provides a boundary condition. So this already includes the fact that you are doing something with a non-trivial with some specification of the boundary conditions at infinity. Because from mass to delta, you're taking a square root, so you have to specify. But I started with delta, so I didn't need to tell you what square root branch I was taking. I can construct m squared from delta. If I start from m squared, then I need to work harder. But if I start from delta, the highest wave state, that's kind of implicitly solving this problem.
David, and all that is because you use specific coordinate system. So what happens?
No, but the point is that this is engineered to build the highest weight state. If you have the highest weight state, you have the full representation. And this is a simple description of the highest weight state in this coordinate system. That's the point.
Okay, you may wish to work with other coordinate systems in AdS.
Yeah, you can change coordinate systems, and then the description can be more or less complicated depending on the change of variables.
Yes, so it means that you will basically always work with this coordinate system.
This is the one that has the nice boundary in the sense that the boundary is a cylinder, it's time and a sphere. And when you look at the metric and you peel off the exponential thing, you actually just get the cylinder.
Yeah, so you really want this.
You want this one.
You work on that coordinate and not another one.
Yeah, so the point is that bulk on shell perturbative solutions can be reconstructed from the boundary. How much time do you need? You only need 2 pi time. Why? Because the coefficients are separated by integers. So you can recover the Fourier expansion by just doing e to the 2 pi I t, sorry, e to the t. And then the natural value is 2 pi. So you don't need to go in time from minus infinity to infinity to recover the thing. It's just a 2 pi slice of time is enough. Okay? So remember, the boundary is a cylinder in the sense that when you take this asymptotics and you factor out the exponential of rows, you actually just get a cylinder for the rest of the coordinates. And this is the natural one. And then what we, yes, okay, we're good. Not far. The boundary is a cylinder. And what that means is that because I'm matching highest weight states to highest weight states, the DDT of the CFT should be the DDT of gravity. That much should be true because I'm trying to match representation theory on both sides. So the list of raising operators and the various partial waves for the thing should be matched by a single particle state to a particular representation of the conformal group. So our simple operator in the CFT is to match the raising operator for a field in AdS, primary to primary, descendant to descendant, in the sense that all delta of 0 should be matched to the raising operator of delta to produce a one particle state of the corresponding field on AdS.
So the DDT is like a Hamiltonian.
The DDT is the Hamiltonian, yes.
That sense, yeah.
Okay. And then what happens is that an operator which is not inserted at the origin is usually going to be a linear combination of A plus A dagger. Why? Because the 2-point function of O is non-trivial in the vacuum, so O needs to have both A and A daggers, so that when you act on Fock space in a canonical quantization, you get a non-trivial correlator. This is the usual thing that fields in Lorentzian theories are usually linear combination of raising and lowering operators. So when you go from minus infinity to some finite time, you get some linear combination rate as a dagger. Okay.
Sorry, one question. If you want to identify the partial T on safety side and the partial T on gravity side, but gravity side you can do coordinate transformation with that.
No, but the coordinate was described by, so what's very important about this is that we did it to match the group theory of SO2,4. And the point is that once you do that carefully, that group theory specified uniquely what the time coordinate is. All of these tricks of these analytic continuations were engineered to actually give the proper notion of time from the point of view of group theory, and that basically gives us the answer. Okay? So the remarks is that for convergence and infinity, what we call delta really needs to be greater than 0, so that the function multiplied by itself, integrated over a spatial slice, is finite. The analytic continuation in T makes the wave equation solutions blow up in infinite fast. So if you take T to IT, I tau, an exponential to the IT with some positive delta, right, becomes an exponential of minus delta times tau, and then when tau goes to minus infinity, this thing blows up. So what happens is that this is the same as the conformal filter intuition, that when you insert something at the origin and you do these analytic continuations, you get some boundary condition when you go to the infinite past where things blow up. So the point is that this intuition is really the same in conformal field theory and in AdS. And this is this kind of Pfeffer-Graham theorem that there's no well-to normalizable solutions in Euclidean AdS. But one of the ways to do it is that really you start from here, you do carefully this stuff, and you see that something is blowing up. But what's blowing up is the solutions of the wave equation, not the list of raising and lowering operators. Okay? So to insert a state in gravity, you can think of it as having a solution to the Euclidean wave equation that has a singularity in the infinite past. And that means you've added a non-trivial boundary condition in the infinite past. And the non-trivial boundary condition is something that's required to, in some sense, produce the state. Okay? So now we're talking the same language in conformal field theory and in gravity, which was not part of the way that Witten described this stuff. It was more. This is moreover, what we usually call in gravity a solution is a classical solution to the equation of motion. In conformal field theory, in quantum field theory, a classical solution should really be represented by a coherent state. This is quantum field theory 101. And then the classical field is proportional to this alpha parameter. When you act with the lowering operator on this, the eigenvalue is alpha. This is the strength of the field in the coherent state formalism. So in our correspondence, this means that this state alpha, that is this classical solution to the equation of motion, needs to be represented as an exponential to some alpha times the operator inserted at 0, because the raising operator was mapped to this thing. And now, what you do is, if you include descendants, the state alpha with all the descendants should be some sum of alpha di, all the derivatives of alpha inserted at 0. And there's another representation for sums of this type, which is an integral of alpha of x O of x over a finite domain near the origin. And then you do the Taylor expansion of alpha and then do that way. So if you do that inside correlations of the field theory, you get that alpha of x is the strength of the source of the function for OX. Okay? Now this is the really important stuff, is that the modified boundary condition in gravity is proportional to the strength of its source, and this is at the level of the solution of the equation of motion. For this stuff, the normalizable part, meaning the decay of this thing, is measuring the state in the bulk. The classical reconstruction of the solution of the equation by partial waves is done by this procedure. So this is the usual story of Witten, that some part recovers the state and some part produces the state. Right? The part that recovers the state can be measured from infinity, and the part that produces the state is a source in the infinite past on the cylinder. Or in some notion of the past in the cylinder. So the normalizable part is what we call the expectation value of the field, which is measured by the expectation value of the operator on the cylinder. Okay. More comments. Multi-particles in the bulk requires a notion of multi-particle in CFT. So I described the single particle state, but I said you have to quantize in the field. So you need to have multi-quanta in the field realized on the dual conformal field theory size. And this is what's usually provided by large N factorization. Large N factorization tells you that there's single trace operators and that you can add their dimensions and that there's some 1/n notion for how these things go.
Okay, so where does n come from? Why? You already agreed that the two Hilbert spaces are the same, so...
No, so the point is that you need a multi-particle in the bulk.
What is n? Where does that come from?
So multi-particle states in the bulk require some notion of multi-particle in the CFT. And I'm saying that if you have large N factorization provides this multi-particle.
But are you assuming now you have a
This is the
CFT
first
with some
mention
large
of that
central
word.
charge? Or
What?
Sorry,
No, I'm assuming that I'm doing semi-classical gravity. So I can do 2, 3 quanta and nothing happened. And the point is that I need to be able to have multi-traces, and that the anomalous dimension for a multi-trace is essentially 0 in some perturbative expansion parameter. That's in some sense the strength of G Newton, and then this is how you match N to G Newton.
That's the answer, but you were trying to
No, look,
explain why we need that.
What I'm trying to say is that you need...
a deeper picture behind
The deeper picture is that you need something that provides multi-partons, and I'm telling you large N is one solution to this multi-parton problem. So large N is a candidate...
There is no n as yet,
There is in the conformal field
only a
theory.
letter at this point.
So you're assuming the CFT theory has a large central charge. Is that the answer? Or?
Yeah, you have to assume that the CFT has a large central charge, so the gravity in the bulk is classical, and then that can translate to some notion of N, and some proper notion of having multi-particle single trace objects or multi-particle states in the CFT, whose dimension is additive.
But then you withdraw that comment that the two Hilbert spaces are the same. Those are not the same.
Well, the point is that there's a Hilbert space that we're constructing in gravity, which is the free field theory on a background. And what does that correspond to? That free field theory implies that some volume has been taken to infinity, or something. Some notion of h bar has gone to 0.
So in the CFT Hilbert space, you have a cutoff, the large n cut, the n cutoff.
Yes.
The exclusion principle.
Yes.
So,
And you need to have a large cutoff.
and where is that in gravity?
Is that you can do effect? No. It's a statement that effective field theory should be a good thing in gravity, and that small perturbations of the classical background should be non-singular as time evolves.
They are not matching up very well, the two Hilbert spaces.
Well, we match the raising operator on one side to some operator on the other one, and we are now matching multi-raising operator to multi-operators.
But now you introduce n, and then you
Yes,
have to
well.
modify things. You have to change your.
No, but the point is single particle state is equivalent to single trace. So what I'm explaining here is, if it's going to work at all, it needs some notion of large N in the sense that
And
multi-particle
single
states.
traces have to be cut off. So
Yes,
But in your group theory, you didn't tell us that.
the group theory doesn't cut off the descendants.
Doesn't,
What,
yeah.
what it cuts off is how many states for some given dimension there are.
Yeah.
And that's not part of the thing that's automatic. Okay.
So should that be part of your AdS dictionary? That's
Well, yeah, eventually it is. So the point is that we need to match something more. But if it's going to work, what you need is that the CFT partition function with a source equal to alpha for the fields, which is what I described, has to be equal to this partition function of gravity with a boundary condition equal to alpha. So this is the stuff that looks like a black box in the usual descriptions of AdS CFT, and I'm telling you that if it's going to work at all, this is the only way in which it can work. Whereas for some people, this is the starting point of AdS CFT. So it cannot work in any other way.
Maybe you can wrap up next.
Yeah. Now it's going to be just standard comments. I have 2 more slides. If you have a continuous symmetry, like d mu j nu equal to 0, it's equivalent in the operator formalism to having a null descendant. And descendants of null are null. This is the usual story of Berman modules and stuff like that of theory. And then there has to have some correspondence in the bulk. So this is something interesting in the bulk in that you need fewer polarizations than a typical particle of a given spin. So one way to get rid of polarizations is that you have to, in some sense, have the particle be massless, because massless representations are the ones that have fewer polarizations per spin. A photon has only a +1 and -1 helicity operator and doesn't have a 0 helicity state, whereas a massive photon does. Okay? So this requires a particle to be massless plus a gauge symmetry that in some sense removes the null state polarizations. So the idea is that the states that would be null in principle are part of the description in terms of fields, and you need a gauge symmetry to say that these things are null and that they're not contributing, and this is what in some sense ties gauge symmetry in the bulk to a conserved charge in the boundary, or a conserved charge in the boundary to a gauge symmetry.
So is there an equivalent way to say this, is that if you have something conserved in the CFT, then it hits some unitarity bound?
Yes. So CFT plus stress tensor. Stress tensor is one of these things that is a conserved charge, must be dual to a theory with a massless spin 2 particle. Why? Because this is the way it works. And if it's massless spin 2, it has to be gravity in the bulk, and it's unavoidable. Okay? You have to do it non-linearly, but the point is that if it's going to work out, it can only work with gravity. So if you have a proper conformal theory with a stress tensor, gravity in the bulk is unavoidable. And then this evidence for the usual law that all symmetries in quantum gravity are gauged. So the bulk is the quantum gravity side, and then the symmetries that we associate in the conformal field theory are the conserved symmetries of the conformal field theory, are the symmetries of the gravity theory, and they all are realized by gauge fields in the bulk. And then this goes to a whole bunch of Lorentz string theory, but this is a very strong evidence for that statement. And if you add SUSY, then you have extra stuff. So you have a bigger symmetry, and then there's BPS states, which are short representations. Shortness is the same thing as hitting some unitarity bound. And it's the same philosophy that if you have null states, you just have some notion of a gauge symmetry or something like that. So they must be massless, not in d+1 dimensions, but in whatever extra dimensions you've added by adding supersymmetry. So BPS equals massless in however many dimensions, so 10d. In type 2B string theory, all massless particles belong to the gravity multiplet. This is a statement about type 2B string theory. So if you get the highest weight state, you reproduce the full tower of states. And then these BPS states must be describable by supergravity solutions, even if they're composite in some sense. Okay. And that's it for today.
Maybe I have a couple of questions. So in the standard way, I mean, a lot is made up of about the double pole structure of the metric and all that. But when you define, I mean, of course, it's there. And
yes.
Automatically, by the way you define the value scaling, I mean,
Yes.
it's happy to get. But in the way you define your actual correspondence with the alpha, that didn't really show up very strongly. That's, I mean, it was kind of hidden.
That's the stuff that was missed by the paper with, in the sense that he decided that this was one way to match it. And now what I'm telling you is that if you're careful about all this stuff, you realize that you cannot do it any other way. Okay? So this black box is defined by some uniqueness of the way that you can do things, which is the stuff that was, I mean, you know, histories are a bit complicated. Sometimes you just spend some time trying to think about why does this work this way, why cannot it be any other way, how can I understand this better, and how do I cheapen some of these calculations so I don't have to read these supergravity papers of various people, and you know. So a lot of this stuff is about, you know, trying to think a bit more carefully about how to think about the symmetry in a nice action of the coordinates. And all of this is hiding a lot of intuition about that as well. Okay? But this double pole structure is kind of the formal mathematical way to define what the boundary is when you're away from the cylinder or from some other things and you have a more complicated metric. That's what helps to define the theory away from m equal flat space or m equal the cylinder. So that's where you need all that. But here you can get around it in some clever way, and it describes how.
Okay, but suppose now I give you some totally warped version of AdS that has no actual global isometries, but locally, is your statement just a local statement?
Well, the statement is that
because locally we have the conformal group.
yeah, the statement is that locally on a very small patch of whatever manifold you're in, we have to have an approximation by something like this. So locally, this structure will be okay, and then globally, all kinds of stuff can happen.
Okay, so it doesn't exclude the warped scenario, that you don't say you have to have pure AdS.
Right. No, if it's going to work for AdS, it has to work this way, and that tells you more or less how it's going to work in all the other
Yeah,
cases.
so totally local AdS that people
Yes.
work is well.
Wasn't also historically there was two dictionaries, one written in France and the other one is, I don't remember, the list of 5 authors.
John of Boyko or?
No. The one was the Banks, that was H, blah blah blah. I don't remember, but it's interpolating dictionary where you take a field and you pull it.
Oh, the extrapolate and interpolate.
Yeah.
Okay, so I did it here, but I just didn't give it names. So it's this statement. So this statement over here is that formal statement. I can recover the solution in the bulk by doing Fourier expansions in the boundary of various kinds. So it means that it gives you an inversion formula from here to here, and that's what the HKLL type of, is it HKLL? Yeah.
No, I thought it's different, but
well, there's a bunch of them, but this is one of those that tells you that there's an integral formula to describe the fields in the bulk by an integral representation on the boundary.
yeah, well, I thought,
Right, this is one of those dictionaries that's out there.
yes, I thought you can also turn on sources, and there was this paper by Stanford and Harlow writes that they need to work a little bit to show the two are equivalent, like a couple of years ago.
Yeah, I guess they had these correlators, they say compute correlators.
Yeah, you compute curves in the bulk and
Take a
then
look
you
at the
extrapolate that.
Yeah, you have to use the extrapolate dictionary and
Yeah,
things, and
yeah.
yes. But this is part of what that stuff
Yeah,
entails.
right.
Well, I couldn't do everything in one lecture.
So, another thing. So you have the state. Assume, let's say we go on a cylinder and you have an eigenstate of Hamiltonian.
Yes.
Eigenstate of Hamiltonian is translation variant.
In time,
And that
yes.
is just a phase.
Yes.
You would seem to be saying that something special happened at minus infinity, but if you have an eigenstate of Hamiltonian, it's all the same.
Well, you have to be careful. This is true in real time. In imaginary time, an eigenstate of the Hamiltonian still blows up everything.
Right.
So that's what happened.
That's what you meant.
So the
Yeah.
eigenstate is invariant in the sense of real time, not imaginary time.
Yes. Yeah.
And that's it.
Yeah, the phase becomes a real factor exponentially growing.
Yes. So what you have is that it's self-similar in that case. That's the
Yes, proportional.
Yes. That's scale.
All right, maybe let's thank David again. And let's start again maybe at 10 past. Is that okay? Yeah, at 10 past.